Hello. Today we will be covering the second half of Chapter 19, Aldehydes and Ketones. So first, we're going to begin with looking at nitrogen nucleophiles. During the first portion of the Chapter 19 lecture, we looked at oxygen nucleophiles, and today we'll be looking at a variety of other nucleophiles, nitrogen, sulfur, carbon, for example. So similar to the reactions that we looked at previously, under acidic conditions, an aldehyde or ketone can react with a primary amine to form an imine. And an imine is a functional group, carbon-nitrogen double bond, and this reaction will require acidic conditions to work. So we can take a look at the mechanism. And the mechanism is fairly similar to our acetal formation mechanism. We're going to have nucleophilic attack, and then this carbon-oxygen double bond will break, and the electrons will go up to the oxygen. Notice the first step is actually not protonation of the ketone in this, even though we're in acidic conditions. And we'll get back to that in a minute. Then the intermediate is protonated, and next a second proton transfer occurs where the nitrogen is deprotonated by the conjugate base of the protonation, and that gives us the carbanolamine intermediate. So this is similar to the hemiacetal intermediate that we saw when we had oxygen nucleophiles. Another proton transfer will create a good living group in the form of water, which can then undergo loss of a leaving group, and finally a proton transfer step to liberate the imine. So even though this reaction is in acidic conditions, the protonation of the carbonyl is not the first step, and that's because the lone pair on the ketone is not the most basic lone pair in the reaction. The most basic lone pair in the reaction is actually the nitrogen on the amine. So amines are bases, and they will consume the proton catalyst, and then our ammonium ion will act as a catalyst for the rest of the reaction. And the ammonium ion with the pKa of 10.5 is not quite acidic enough to protonate the aldehyde or ketone oxygen, but it is acidic enough to do the proton transfer step in this second step here. So you can see based on this ammonium ion formation that the pH of this reaction is extremely important for the reaction to occur. And there's a sweet spot right around pH of 5 that the reaction will be at the fastest rate. At a low pH, all of the amines are protonated, and we'll have no amine that's available for nucleophilic attack. And then at high pH, we have not enough acid to catalyze the reaction efficiently. So we do want to maintain a pH of right around 5 for this reaction to occur. If we have a secondary amine, we're going to obtain a different reaction. In the case of a secondary amine reacting with a ketone, we will form an enamine. And so the mechanism of this is similar to the imine formation mechanism, but there's a small difference at the last step. So to begin with, we have nucleophilic attack of the ketone, protonation, followed by a proton transfer, and that creates the carbanolamine. This is all the same up until here. Then we have another proton transfer and loss of the leaving group, and that gets us to this intermediate. So in the primary amine stage here, we had a proton where this R group was, and we deprotonated. But in the case of a secondary amine, we no longer have a proton there, so the proton transfer step from the base is actually going to be on the alpha proton, and that will form the enamine. So we can compare and contrast these two mechanisms and see that up until the penultimate intermediate, they're the same. We then have the deprotonation of the imine on the primary amine mechanism, and we have deprotonation of the beta hydrogen on the enamine formation mechanism. The next reaction that we're going to look at, which undergoes a similar mechanism for the first stage of the last two, is the Wolff-Kishner reduction. In a Wolff-Kishner reduction, we are going to learn a reaction where we can take a ketone and convert it all the way to the alkane. And this is going to go through this imine intermediate with hydrazine, so two nitrogens, two amines bonded together. This intermediate is actually called a hydrazone. And then we undergo an elimination reaction to form the alkane. So in the first step, we have the formation of the imine, and this is going to be the same mechanism that we looked at for the formation of a primary imine. So you can refer to the mechanism a couple slides ago to get to this stage where we have the hydrazone intermediate. Then the base of the hydrazone intermediate will deprotonate the amine and will push electrons down to the carbonyl carbon. This carbon then has a negative charge, can be protonated, which creates this azine intermediate. Another proton transfer allows nitrogen to leave as a gas. So at this stage, we're able to expel nitrogen as our leaving group, and that puts a negative charge on the carbon, which can then be protonated and form our alkane. All of these reactions that we've looked up until this point have a lot of similarities, but one thing that we should note and that we discussed in class in person, is that under acidic conditions, we should be dealing with only neutral and +1 formal charges. None of the intermediates, except for that brief intermediate on the imine formation, should have a negative charge. In acidic conditions, we're looking at mostly positively or neutrally charged species. The next reaction that we'll look at is the hydrolysis of the acetal, and this is pretty much the reverse reaction of the acetal formation reaction. So in acidic conditions, we're able to convert the acetal back into the ketone. And if you recall the synthesis that we did where we used the acetal as a protecting group, the final stage of the synthesis was this acid catalyzed hydrolysis. So under acidic conditions, acetals will react with water to form the ketone. Under basic conditions, no reaction will occur. So acidic conditions are required for this reverse reaction to occur. And if we look at the mechanism, you'll notice that this is more or less the reverse of the mechanism that we used to form the acetal. Our first step, a proton transfer, will create a good leaving group. Then we can reform the carbonyl through loss of the leaving group, and then water acts as a nucleophile on the carbonyl. Another proton transfer will form our hemiacetal. Another proton transfer will form once again a good leaving group, which allows us to reform our carbonyl, and a proton transfer liberates the ketone. This same hydrolysis reaction can occur for both imines and enamines, and the mechanism for these two reactions will be the reverse of the mechanisms for their formation. And notice that in these cases, instead of having excess amine and acid, we'll have excess water and acid, and this will push the equilibrium in the opposite direction to reform the ketone. Sulfur is very similar to oxygen when it comes to its nucleophilicity and its reaction with ketones and aldehydes. So we can create a thioacetal from the sulfur analogs and a cyclic thioacetal using the same mechanism that we used for acetal and the cyclic acetal formation with oxygen. And one interesting sequence that we can use these thioacetal intermediates for is the conversion of a ketone to an alkane. So we already looked at the Wolff-Kishner reduction, which allows us to convert the ketone to the alkane through the hydrazone intermediate. Thioacetals can be directly converted to an alkane using Raney nickel. So this allows for another method for the reduction of a ketone or aldehyde to the alkane, first forming the thioacetal, and then second the reduction with Raney nickel. Now this next section is mostly review from reactions that we've already seen when we looked at the alcohol chapter 12. We can take an aldehyde or ketone and reduce it to the alcohol with a hydride reagent. We learned about lithium aluminum hydride and sodium borohydride functioning as these hydride delivery agents. So if we take the ketone and subject it to lithium aluminum hydride followed by water, or sodium borohydride followed by methanol, we're able to obtain the alcohol. And these reactions have strong nucleophiles, so we're able to execute them in basic conditions. And just a review of the mechanism, the hydride will attack the ketone, and that opens up as an O-, which then, after a proton transfer, will form the alcohol. And in an unsymmetrical ketone, this reduction will result in a racemic mixture of two stereoisomers. Another reaction that we can review is the Grignard reaction. This is a reaction that we can use to form a new carbon-carbon bond. And it'll have the same, more or less the same mechanism that we just looked at for hydride. We're going to use our methyl Grignard here to form a new carbon-carbon bond and a methyl group, and that creates a tertiary alcohol. And in the presence of an aldehyde, we can form a secondary alcohol. Mechanism, whatever Grignard reagent we have attacks the carbonyl carbon, pops open the ketone, which then can form the alcohol through a proton transfer. And this is consistent with the basic condition mechanism that we looked at, similar to the hydride mechanism. Now a new reaction that we'll look at is the cyanohydrin formation reaction. I know we looked at using cyanide as a nucleophile when we looked at SN2, but I don't think we've looked at using cyanide as a nucleophile for ketones yet. So a HCN, hydrogen cyanide, can react with a ketone to form a cyanohydrin, and you can see that HCN has added across the carbon-oxygen double bond. And once again, we'll be using basic conditions for this reactions. Our first step is going to be nucleophilic attack of the cyanide ion, and that will form our new carbon-carbon bond. And then our second step will be a proton transfer to yield the cyanohydrin. In order for us to run this reaction in basic conditions, we're going to add a little bit of potassium cyanide as well as the HCN. And this way we have more of the cyanide ion than the proton. So we'll use a buffer system of potassium cyanide and hydrogen cyanide to obtain our product. Now, one of the interesting aspects of this reaction is that we can take the product and hydrolyze it into a couple of other functional groups. So once we've obtained the cyanohydrin, if we use lithium aluminum hydride, we can reduce the cyano group to a primary amine, or if we treat it with acid and heat, we can hydrolyze to the carboxylic acid. So this is a way to obtain a carboxylic acid functional group attached directly to the same carbon as an alcohol, or a 1,2 alcohol amine relationship. Now, the next reaction we're going to look at is it's actually a series of reactions we're going to look at that are new carbon nucleophiles. And this is called the Wittig reaction. It's an extremely important reaction in organic chemistry because it allows us to build larger carbon skeletons. In this reaction, we're going to convert a ketone or aldehyde into an alkene with a new carbon-carbon double bond. And we can actually use different lengths of Wittig reagents to form different lengths of alkene chains here. So in just the simple reaction that we're looking at here, the simple substrate, we're just adding one methyl group, but we can actually add a lot larger carbon groups to our ketone. So the Wittig reagent is a phosphorus ylide, or an ylide is a neutral compound that contains both a negatively charged atom adjacent to a positively charged atom. So in this case, we have a negative charge on our carbon and a positive charge on our phosphorus. The mechanism that we'll be undergoing is a mechanism similar to the cycloaddition mechanisms that we looked at, and it'll be between the Wittig reagent and the carbonyl group. And we can take a look at that mechanism. We'll have the oxygen form a bond with the phosphorus, and the carbon with the negative charge forming a bond with our partial positive carbonyl carbon. And this creates a four-membered ring intermediate, which can then fragment into a new alkene and the triphenylphosphine oxide. And the driving force behind this reaction is the formation of this triphenylphosphine oxide because this is an extremely stable compound. We have an SN2 reaction where the triphenylphosphine attacks the alkyl halide and the bromine leaves. Then this phosphonium salt will be deprotonated by the strongly basic butyl lithium, and that will create our Wittig reagent. When we go to add and execute the Wittig reaction, we're going to form our new carbon-carbon bond, and we're actually going to have some stereoselectivity with this reaction, as it will give the Z isomer, the Z alkene, as the major product. And that's if we're using a Wittig reagent derived from a simple alkyl halide. We'll form the Z alkene. So this is an ethyl Wittig. We're adding two carbons here. And you can see these two carbons in the product. And you can see between the methyl and phenyl, we have them on the same side of the alkene. So that is a Z product. Now, we can reverse the electronics of the Wittig reaction. In this case, we do that by adding an electron withdrawing group to the Wittig reagent. So here our Wittig reagent has an ester group attached to it. And so if we add an electron withdrawing group, we're going to observe the opposite stereochemistry. In this case, we will obtain the E isomer as the major product. In the second case we looked at with the electron withdrawing group, the phenyl ring or electron withdrawing group will delocalize the anionic charge of the Wittig reagent, which makes it more stable, and this results in the E alkene product. There is another reagent that we can use, which is similar, called the Horner-Wadsworth-Emmons reagent, and this reaction will employ a reagent similar to a stabilized Wittig reagent and also gives the E alkene as the major product. So here's the example we looked at where the Wittig reagent had the ester group stabilizing the negative charge. And in a Horner-Wadsworth-Emmons reagent, you can see we've modified our phosphonate to a phosphonate ester, and this is going to stabilize the carbanion even more. So an example of a reaction employing a HWE reagent will give the E alkene as our major product, similar to the Wittig reagent. When we go to make our Wittig reagent and decide, okay, for this particular molecule, which Wittig reagent do we want to use, there's actually going to be two potential options depending on which side of the double bond we use as our ketone and which side we use as a Wittig reagent. So if we just look at this target molecule, we could see in one route it would start with the ketone on the left and this simple Wittig reagent. If we swap sides, we could use also formaldehyde and this Wittig reagent. So in order for us to examine these two routes and decide which one will be better, we have to think about the alkyl halide needed to make these two reagents. In the first route, we will just use a methyl halide, and in the second route, we would use a secondary halide. So in this case, we would go with the first route because the SN2 reaction of an alkyl halide like methyl is going to be much better than a secondary halide undergoing an SN2 reaction. So here we can use methyl iodide and create our Wittig reagent and then subject it to this ketone to obtain our alkene. The final reaction that we will look at today is the Baeyer-Villiger oxidation. In this reaction, we're going to insert an oxygen next to the carbonyl carbon in a ketone or aldehyde. The mechanism for this reaction begins with the peroxide attacking the carbonyl carbon. So the oxygen in the peroxide acts as our nucleophile, attacks the carbonyl group, which pops open the carbonyl. And then we have a proton transfer occur to form a neutral species here. The ketone can then collapse back down and a rearrangement occurs. So we have an alkyl shift. You've seen an alkyl shift before when we looked at carbocation rearrangements to form more stable carbocations. So this R group shifts over to the oxygen, and then this acetyl group leaves. If we have a cyclic ketone, under these conditions, we'll form a lactone. And the rate of migration is going to be that a proton transfers quicker than a tertiary carbon, which is quicker than a secondary or a phenyl, quicker than a methyl or a primary.